In this video I will explain exercise 11.3, in which we will find the stoichiometric coefficients by solving a linear algebra problem. We will follow the 3 steps of coding, starting with step 1, defining our problem. We are given a stoichiometric reaction of the oxidation of pyrite by the bacterium Leptospirillum. Our task is to find the 8 unknown stoichiometric coefficients A, B, C, D, E, F, G and H. Now we can continue to step 2. How are we going to solve this assignment? We have 8 unknowns, thus we will need 8 equations to find all 8 stoichiometric coefficients. Let's first write out the element conservation equations. Let's start by writing out the carbon balance. Carbon only occurs in carbon dioxide and biomass, thus we put a 0 in front of the other coefficients. In the same way, we also write out the hydrogen, oxygen, nitrogen, sulfur and iron balances. And we can add the charge balance as well. As you can see, these are all linear equations, thus we can write them in matrix notation. This gives us the matrix of known coefficients, the vector of unknowns and the right-hand side vector of knowns, in this case 0. You should notice that we have written out 7 equations, but we have 8 unknowns. Let's check how many independent reactions we have by finding the rank of matrix A in MATLAB. First we write out our matrix. To find the rank of our matrix, we simply type rank of A and run our script. We find that the rank of our matrix A is 7. This tells us that all 7 equations are independent. Thus, as we have 8 unknowns, we have an undetermined system with 1 variable. Let's choose D as independent variable. To solve the system, we have to separate the dependent part, D and 1 for biomass, from the independent part of the matrix. We can solve this system symbolically in MATLAB by expressing the unknowns as a function of D. We can do this by solving this formula. Let's do this in MATLAB now. We've already typed our matrix A in MATLAB. We can define our AD and AF matrices by indicating which columns of A we want to select. Therefore we can use this notation. All rows of column 1, 2, 3, 5, 6, 7 and 8 for AD and all rows of 4 and 9 for AF. We also have to define our vector xf. However, until now D is undefined. Thus we have to tell MATLAB to use D as a symbol by writing the command simsd above xf. Now we have to write the equation to find xd and run the script, and we find a symbolic solution. Let's assume that we know that the yield of oxygen on substrate D is 0.05 mole oxygen per cmol biomass. Notice that I use a minus. It is oxygen consumption. Then we can fill in D in symbolic solution to find the other coefficients. We can do this by substituting the symbolic D by the value minus 0.05. The outcome is in fractures. We can change that with the command double. Let's analyze the solution we obtained. We see that A, B, D and H are negative. Thus we have iron sulfate, carbon dioxide, ammonium and water consumption, and proton biomass and ferric iron production, which seems alright. We could also have chosen to express the coefficients as a function of F instead of D. Let's see what happens then. Now we have to change our matrices AD and AF and the vector xf. We now want to put the 6th column in the AF matrix instead of the 4th, and we change xf to include F instead of D. Now the solution is given as a function of F. Now that we've set the oxygen yield, we could also have solved the system numerically. We can still use the 6 element balances and the charge balance, but now we can add the extra information as a new equation in our system. So in principle we now have 8 equations and 8 unknown. We can adapt the matrix to include D is minus 0.05. We will add a 1 in our A matrix for D and minus 0.05 in our B vector. We want to separate all the knowns on the right hand side of the matrix, so the biomass formation. This gives us the following system. We can simply solve it by using x is A over B. Let's try this in MATLAB and compare the 2 solutions. We can copy matrix A from our previous script. We need to remove the last column because we have separated the knowns in the B vector, and we can add an extra row for D is minus 0.05. Then we write out B, take care of the minuses for the biomass coefficients, and we add minus 0.05 for our new equation. Now we can simply write out x is A over B. but something went wrong. We get an error message. The vector b has to be a column vector, so we have to change that. And I also forgot one of the minuses in the b vector. Now we find the solution. And let's compare this to the symbolic solution. You can see that it's the same. However, you can also notice that the numerical solution is a little bit faster. It's not so noticeable for such a small system, but for larger systems it definitely will.